So fine. First, we will try to do the 8.1 for the basic comparator of figure 8.1a. Vin is equal to 2 volts peak-to-peak sine wave at 1 kilohertz. V reference is 500 millivolts, R equal to 100 ohms. Supply voltage plus or minus 15 volts. Draw the output waveform. So for this is the, what you call comparator he's talking about. You can see that here reference voltage is connected to the minus and the input is connected to the plus. So when input is connected to the plus and the reference voltage is connected to the minus, okay, with the protective diodes over here, then this is known as the non-inverting or positive, comparator. Non-inverting or positive comparator, because input is given to positive. Okay. So when the input is high, the output also will be high. Rather, you can say if the input is higher than the V reference value, then the output will be high. When the input is lower than the V reference value, the output will be low. Okay, that is the idea behind that. So in this figure, you might have taken the value of the V, peak-to-peak value to be here something like 8 volts. Okay, here he has taken 8 volts, and he has taken the value of the reference value to be 1 volt. Okay, reference value is 1 volt. Peak-to-peak is 8 because this might be 4 and this might be 4. 4 plus 4 will become 8, and the reference value is 1. So for the portion for which it is more than the V reference value, the output is high. Output is high. For the portion for which the input is lower than the reference value, that is this one, the output is low. Output is low. Okay. Now that is the value over here. Similarly, for a negative value of V reference also, you can see over here, right? For the portion of the input for which the input is more than V reference, that is this portion till this, okay, till this, it is high. For the rest of the portion from here to here, that is here, right, it will be low. So again from here till here, it will be high. For the rest of the portion, again from here till might be here, it will be low. Okay, for some part. So thus you need to write for this also in the same way. Here only that it is V in is 2 volts peak to peak, that is V maximum will be half of that. Peak to peak value will be twice of the V maximum. V maximum will be 1 volt. Reference will be 500 millivolts. So in place of 4 volts here, this will be 2 volts, and the V reference value should be 500 millivolts, that is 0.5 volts, which will be exactly in the middle. Okay, 0.5 volts, which will be exactly in the middle. So for only this portion, right, for only this portion, the input will be high. For the rest of the portion from here to here, the output will be low. Okay, from the portion here to here, the output will be high. For the portion from here to here, output will be low. Okay, that's all is what you need to draw. So this figure will change accordingly, right? From here to here, it will be high. From here to here, the output will be low. Then we go for the next one, that is repeat the problem for the V reference equal to minus 0.1 volt. Okay, repeat the problem for the V reference equal to minus 0.1 volt. So minus 0.1 volt just means that we are again at the same place, right? The peak value being 1 and minus peak value minus V maximum is minus 1. So minus 1 will have the reference, that is in place of 1 here we will have at minus 1 here we will have minus 0.1. Okay, minus 0.1. So minus 0.1 just means for the portion of the input for which the input is more than the minus 0.1 volts, the output will be high, and for the portion of the input for which the input is lesser than the V reference, the output will be again low. So it will be similar to this, only that this will be 0.1 minus 0.1, and this will be minus 1 volt, and this will be plus 1 volt. That's all, and accordingly you need to write that. The what you call values here, high and low, will be plus Vsat and minus Vsat, plus Vsat and minus Vsat. Okay, so that will be the case over there, right? So I'll just repeat the same thing. So for this, what we have is the 8.3 is for the inverting comparator, we have Vin is equal to 1 volt peak to peak. That means Vp or Vmax will be equal to 0.5 volts. And we need to consider the inverting comparator, V reference equal to 0.2. So inverting comparator is here. Inverting comparator is here, where we have connected the input to the minus and V reference to the plus. So for the values of the what you call input above the V reference, output will be negative. For the values of the input below the V reference, output will be positive. Even here also same thing. So for all these three values, for all the three values of the input, 0.2 volts, minus 0.2 volts, and 0 volts, we need to write the waveforms here. Okay, we need to write the waveforms here. So whenever the input is more than the reference value, output will become negative. Whenever the V reference value is lesser than the when the input value is lesser than the V reference, output will become positive. Okay, for a inverting comparator. For a inverting comparator, you can see that this is a inverting comparator, and that is what we have here, the inverting comparator in the question also, right? Inverting comparator. Now let us go for the next one. For the zero crossing detector shown in the figure 8.3a, draw the output. Okay, draw the output waveform. If the input is 500 millivolts peak to peak sine wave at 1 kilohertz, at 1 kilohertz. Okay, so 8.3a we should be able to go. 8.3a is the figure which is here. Okay, so now the V reference is 0 connected to ground, which is at plus. Okay, input is connected to the negative here again, and plus is connected to ground. So again, it is a what you call zero crossing detector, but it will just invert, because again we are connecting to input. Input is connected to minus, and plus is connected to ground, so naturally it is supposed to invert. So you can see that the waveform here is for the values which are positive of the input, the output is negative. For the values of the input which are negative, the output is positive. Okay, so reference is 0 here for the zero crossing detector. So in the problem, if we just see there, right, output waveform, if the input is 500 millivolts peak to peak, so that means 0.5 millivolts peak to peak. So that will give us the peak as 0.25. Half of this peak to peak is 0.5, means 0.25 will be the peak value, and for the positive portion of the sine wave, the output will be minus V reference. For the negative portion of the sine wave, output will be the plus V reference. Okay, that is what is shown over here, right? That is what is shown over here. Now let us go to the next problem. It's a little invisible, so therefore I'll tell the values. Please write down those values. Okay, so they are missing from the whatever photocopy we have taken. So therefore here it is R1 equal to 150 ohms. Please write down this. R2 is equal to 68K. V input is equal to 500 millivolts peak to peak sine wave. Okay, what is invisible is R2 equal to 68K and V in equal to 500 millivolts, 500 millivolts peak to peak. Okay, these things are invisible. Other things are visible as it is. The saturation voltage is plus or minus 14 volts. Determine the DC threshold voltage, VUT and VLT, and what is the value of the hysteresis voltage. So you need to find the VUT and the VLT given the value of R1, R2, and the input is 500 millivolts peak to peak. Okay, so if V input is 500 millivolts peak to peak, VP will be equal to 250 millivolts, that is equal to 0.25 millivolts peak. Okay, just peak. Okay, half of that. And R2 is 68K, R1 is 150 ohms. Okay, 150 ohms, and the saturation voltage is 14 volts. So we need to see the 8.4A over here, 8.4A. So this is the Smith trigger. Okay, you can see that this is almost similar to our, what non-inverting amplifier. The figure is almost same as non-inverting amplifier, except that input is given to the minus, and to the positive we are connecting the potential divider network. Between the positive and between the output and the positive, we are connecting the potential divider network. If you just change this to plus and this to minus, it will become a non-inverting amplifier. So don't do that. If this is plus and this is minus, then it is a non-inverting amplifier. Okay, so non-inverting amplifier. So in the test, as I said, values will be might be changed, and also you might be asked to draw the figure corresponding to that and waveforms and whatever values are there. Okay, so here we need to find the VUT and VLT. So you can see that whatever we have here, all those values, VLT, VUT is calculated, and then try to write that. Okay, so I'll just expand it a little. It might be it is too small. Okay, this is VUT and this is VLT, right? This is VUT and this is VLT. Okay, so VUT and VLT. So between this, VUT and VLT positive portion, you have the output as negative. Between the VLT and the VUT in the negative portion over here, we have it as plus VSAT. Okay, and we'll get the figure which is something like this. The hysteresis curve will get something like this. Okay, we'll get the hysteresis curve which is something like this. Okay, so we need to find the values there. Let us see the formula for that. So VUT is R1 by R1 plus R2 plus VSAT. So here the input voltage has no meaning at all. Please remember that for VUT and VLT calculation, it is the VSAT. So plus VSAT is 14 volts. R1 is given to us as the 150 ohms, and R2 is 68K. 68K. You need to write 68,000, right? So in the this one R1 is 150 ohms, 150 ohms. This is 68,000, and this is 14. So find the value of VUT. Similarly, find the value of VLT. VLT will be again R1, which is 150, divided by 150 plus 68,000 into minus 14 into minus 14. Okay, so corresponding to that, we will have the waveform which will be here like this. So these are the things, and then we need to take for the portion between this to this is negative, and for the portion between this to this, it will be output will be positive. Okay, that is the numerical there, right? So determine the threshold voltage VUT and VLT, and if you are asked to plot, you can plot that also. Then what is the value of the hysteresis voltage VHY? So VHY is just nothing but VUT minus of VLT. VUT minus of VLT. That is the value of the hysteresis value. VUT minus VLT. Just subtract the smaller value from the larger value, negative value from the positive value, which will be naturally twice of that. Okay, magnitude wise it will be twice of VUT or VLT. Okay, next we go to the next problem, 8.6. Repeat the problem 8.5 with R1 equal to 100 ohms and R2 equal to 3.9 kilo ohms. So 100 divided by 100 plus 3,900 into 14 will be VUT. 100 by 100 plus 3,900 into minus 14 will be VLT. And the hysteresis value will be double of the VUT itself. Okay, because V hysteresis is positive. Okay, that will be 8.6. Is there? So here we have just finished the 8.6. We'll go for the 8.7. Okay, 8.7. 8.7. What is 8.7? In the circuit of 8.5, Vin is equal to 100 millivolts, peak sine wave, R1 equal to this, diodes are this, the op amp is 741, draw the output voltage waveform. Okay, so this is, I think, we don't have this in our syllabus. 8.5, let us see what is 8.5. Yes, so this is out of the scope of the syllabus, so we need not bother about this. These are comparators with Zeners. Okay, we will not do that. Limiting, I think, might be it is limiting. Okay. Oh, yes, voltage limiters. That is not in our syllabus, so don't bother about that, right? So we'll go for the next part, that is the syllabus corresponding to. So we are finished with the what you call syllabus here is comparator, zero crossing detector, and the Smith trigger. Okay, these are over. So till now we are finished with the module 4. Module 4. Okay, so we'll stop at this for the time being.